Okay, so imagine this for a moment. Something about reality doesn't fully make sense yet, not in a poetic way, not as a metaphor, in a very literal physical sense. Number 10, the measurement problem. Take one of the simplest experiments in physics, an electron, a barrier with two slits, a screen behind it, no observers, no cameras watching in real time, just the setup. You fire the electron. According to quantum mechanics, it doesn't go through one slit or the other. It behaves like a spread out wave, passing through both at once. Repeat the experiment many times and you don't get two lines. You get an interference pattern, the signature of a wave interfering with itself. This result is extremely well established. It's been reproduced with electrons, photons, atoms, even large molecules. Now, change just one thing. Place a detector to measure which slit the particle goes through. You don't change the particle. You don't change its energy. You just measure. The interference pattern disappears. The system behaves like a classical particle. One path, one result. What matters here is subtle. It's not about a human watching. It's about whether the system can, in principle, record the path. One interpretation suggests that interaction with the environment, what we call measurement, breaks the superposition. Other interpretations propose entirely different pictures, multiple realities, hidden variables, or deeper structures we don't yet see. There's no consensus, but the experimental fact remains. Before measurement, we describe possibilities. After measurement, we observe a single outcome. Why the result depends on how we measure the system is still one of the biggest open questions in physics. Number 9, delayed choice, retrocausality. Now push that idea further. What if the timing of the measurement matters? In delayed choice experiments, particles pass through the slits, and only afterward we decide how to measure them. That decision is often made using random generators at the last possible moment. The results still match quantum predictions. If we measure path to particle behavior, if we don't to wave pattern. Some interpretations describe this as if the outcome depends on choices made later, not because the future literally sends signals to the past. There's no evidence of that, but because the way we describe the past depends on how the experiment is completed. Physicists are careful here. This doesn't mean causality is broken, but it does suggest that our everyday idea of time, past determines future, might not be the full story. Number 8, quantum tunneling. Now consider something even stranger. A particle approaches a barrier. Classically, if it doesn't have enough energy, it stops. But quantum mechanics allows something else, a probability that the particle appears on the other side. No visible crossing, no added energy, just there. This is quantum tunneling, and it's not rare, it's essential. The sun shines because of it. Nuclear fusion depends on it. Modern electronics must account for it. Without tunneling, the universe would look completely different. At human scales, the probability is effectively zero, but not mathematically impossible, which suggests something subtle. Barriers aren't absolute, they're statistical. Number 7, non-locality entanglement. Now let's talk about distance. When two particles become entangled, their properties become correlated. Measure one, and the other's result is instantly related, even across vast distances. Experiments, starting with those by Alain Aspect, have confirmed this behavior repeatedly. Modern setups use satellites separating particles by hundreds or thousands of kilometers. The correlations remain. Important clarification: no usable signal travels faster than light. Nothing we can measure carries information instantly, but the correlations themselves cannot be explained by simple local models. One interpretation suggests we shouldn't think of the particles as separate objects at all, but as parts of a single system. Whatever the explanation is, it doesn't fit comfortably with the idea that everything is strictly local. Number 6, fine tuning. Now zoom out. Look at the universe itself. Physics relies on constants: gravity, charge, mass, expansion rate. We don't derive these values, we measure them. What's striking is this: many of them fall within extremely narrow ranges that allow stars, atoms, and chemistry to exist. Change them slightly, and the universe could become unstable, empty, or chaotic. Why? There are several interpretations. The anthropic principle: we observe this universe because it allows observers. Deeper physical laws we don't yet understand. Or something else entirely. There's no consensus, but the precision is real. Number 5, dark matter. Now consider something even more direct. Galaxies rotate too fast. Based on visible matter alone, they should fly apart. They don't. One explanation: unseen mass, dark matter. It doesn't emit light, doesn't interact electromagnetically, but exerts gravity. It helps explain galaxy rotation, gravitational lensing, large-scale structure formation. Models suggest it could make up about a quarter of the universe's energy content. And yet, we haven't directly detected it. The equations work. The evidence is indirect. The nature of it remains unknown. Number 4, vacuum energy. Even empty space might not be empty. Quantum field theory predicts fluctuations, temporary particle pairs appearing and disappearing. This implies vacuum energy. Effects like the Casimir force support aspects of this idea. But there's a problem. Theoretical predictions of vacuum energy are vastly larger than what cosmology observes. Not slightly off, off by enormous margins. And yet the universe still exists, which suggests either our calculations are incomplete or something cancels most of that energy out. We don't know how. Number 3, pilot wave interpretation. Some physicists have proposed maybe quantum mechanics isn't incomplete, just incomplete in interpretation. The pilot wave theory suggests particles are real objects guided by a wave-like field. It reproduces known results, but introduces deeper structure. Interestingly, some classical experiments, like oil droplets bouncing on vibrating surfaces, show behaviors that resemble quantum patterns. These analogies don't prove the theory, but they show something important. Quantum-like behavior might emerge from deeper systems. Number 2, quantum biology. Quantum effects may not be limited to labs. There's evidence, still debated, that biological systems might use them. Photosynthesis, for example, may involve quantum coherence to optimize energy transfer. Some studies suggest birds might use quantum effects to sense Earth's magnetic field. These ideas are still under investigation, but if confirmed, they would blur the boundary between quantum physics and everyday life. Number 1, consciousness. And then there's this. Physics can describe particles, fields, galaxies, but it doesn't yet explain something fundamental: why any of it is experienced at all. Not what the brain does, but what it feels like to be. This is often called the hard problem of consciousness. Some theories treat consciousness as emergent, others speculate about deeper connections. But here we need to be precise. There is no scientific consensus linking consciousness directly to quantum mechanics. What we can say is this: quantum mechanics shows that measurement matters, but what counts as an observer and how experience arises remains an open question. Take a moment. An electron behaves differently depending on how it's measured. Some experiments challenge how we think about time. Particles cross barriers they shouldn't cross. Systems act connected across distance. The universe runs on constants we don't fully explain. Most of its matter is invisible. Even empty space doesn't behave as expected. Life may use quantum effects, and consciousness remains unexplained. Our models are incredibly precise, but interpretation is still evolving. Maybe nothing is wrong with reality. Maybe we're still learning how to read it. And if you don't want these questions to disappear into silence, stay here. There's more we haven't understood yet. And remember, the universe doesn't reveal its secrets to those who rush. It reveals them to those who know how to observe what others ignore. Subscribe and keep listening to the silence.